Well, good morning, everybody. I'm Michael Ossmann at Gray Scott Gadgets, and it's great to see you all here this morning. And thanks to Black Hat for having me again here at Black Hat Asia. It's always a treat to be here and to get to meet some folks that sometimes I don't otherwise get a chance to meet in other parts of the world. I'm talking today about rapid radio reversing, and this is reverse engineering of digital radio communication systems, and in particular doing over-the-air reverse engineering. So there are a lot of ways to reverse engineer things. A lot of people think of reverse engineering as being a software discipline. Some people think of reverse engineering as being a hardware discipline. But I'm talking about reverse engineering of radio signals. So figuring out how a radio communication system works or how a protocol works simply by making observations of the over-the-air signals and not directly attacking hardware or software, simply by observing radio signals and interacting with the system that way. So I want to talk in particular today about an approach to radio reversing that uses both software-defined radio techniques and non-software-defined radio techniques. And software-defined radio is, of course, the technique of using digital signal processing to implement radio functions in software that would otherwise have to be implemented in hardware. And software-defined radio is the most powerful tool for wireless reverse engineering. It is the tool that you need to get to know if you want to be an expert wireless reverse engineer, if you want to be able to analyze any radio system under the sun, then you need to be familiar with SDR. But there are a lot of radio communication systems, especially these days, a huge proliferation of low-cost, low-speed digital radio systems in things, ranging from industrial settings, home settings, etc. And many of these things can be implemented, or their communications can be implemented using non-SDR tools, in particular using wireless transceiver ICs that are capable of implementing digital radio communications just on a single chip. So sometimes those tools are more appropriate or easier to use for a particular job. And I want to show you today an example of how you can reverse engineer a radio system using SDR for parts of the process of reversing where it's most convenient, and other tools for parts of the process where that's more convenient. The SDR platform I'm using today is HackRF1. I like it because I designed it, so I'm totally biased. But it serves as really just an example. The stuff I'm going to do today could be done with a whole bunch of different SDR platforms. This is just the one that I'm using. And it digitizes bandwidth. I'm going to be using it just as a receiver, not as a transmitter today. And so as a receiver, what it does is you connect an antenna to it, and it samples or digitizes the radio waveform that it's receiving, and then gives me over USB connection to my host computer a digital signal that is representative of the analog waveform, kind of like a sound card, but about 1,000 times faster, so that it can sample radio waveforms instead of sound waveforms. And the great thing that SDR allows us to do is that it completely represents what happened. It captures everything that happens in a radio signal or over the air within a certain bandwidth at a certain frequency over the capture period of time. So it gives us sort of a chunk of information about the radio spectrum that is sort of a complete description as opposed to just an interpretation. And we'll see what that looks like in a little bit. And SDR has a number of strengths that I mentioned, and in particular, the greatest strength is that it's universal. You can implement any kind of modulation with software-defined radio because it It is completely describing everything that happens in that bandwidth for a period of time. And so any modulation that fits within that fixed amount of bandwidth can be implemented with a software modem in software on my laptop. And it's SDR, when you are doing reverse engineering, it's particularly handy. It makes it easy to detect the precise frequency of transmission of the system. It makes it easy to reverse engineer the modulation, to detect or figure out what the modulation is. And SDR also is extremely good at replay. I can capture a radio signal and replay it without even having to analyze it, just like hitting record on a tape recorder and then playing it again. So it has a bunch of strengths that are really nice for reverse engineer, but it has some weaknesses too. SDR has a steep learning curve. It really does take a lot of effort to learn all you need to know about software-defined radio. I do a 2-day class that is very intense, and it just kind of gets people going up this curve so that they can start to experiment with things on their own. But really, you need to learn a lot about digital signal processing in order to effectively use software-defined radio to reverse engineer arbitrary wireless communication systems. And it's really good at dealing with the physical layer, but once you start going up the protocol stack, once you start dealing with packet data as opposed to waveform data, it becomes more difficult to use. And it's slower. For the reverse engineer, it's slower to use SDR once you start going up above the physical layer compared to some non-SDR tools. Now, this is the tool that I'm going to use as my example for non-SDR. This is Yardstick 1, and once again, this is a board that I designed, so I'm totally biased, but this is an example of a platform that features a wireless transceiver IC. It's that chip, the biggest black square there near the middle of the board. That's called the CC1111, and it's one of many wireless transceiver chips that are on the market that are affordable and can be found on all sorts of different development boards that you can buy, or tools like Yardstick 1 that you can buy, or that are embedded into all manner of different radio products. So including one that I'll be reversing today for you. I don't think the one I'm reversing today has a CC1111, but it has another chip that is kind of similar to the CC1111. The CC1111 is almost the same chip that's in my favorite pink toy, the IM-Me. That actually has a CC1110. This CC1111 is the exact same radio, exact same microcontroller. The only difference is that it adds a USB interface. So I'm able to make a little dongle out of it that gives my host computer a radio interface via USB. And the key thing to know about the CC1111 or any of these wireless transceiver ICs that are on the market is that they provide a digital modem on a chip. So all the modulation and demodulation is done in hardware, not in software. With SDR, we do that stuff in software. With something like this, we do that in hardware. And so it's more limited. It's not so universal as software-defined radio. But it does a lot of the heavy lifting for us. So for those radio communication protocols that are compatible with this particular modem, it's very convenient and quick and easy to use. So for certain aspects, certain parts of the radio reverse engineering process, we're going to use this today, just kind of show how it's more convenient for certain things. Now you might be wondering, what types of systems, what types of radio systems is this compatible with? And I can't even give you a comprehensive list because it's so long. This particular part is designed for sub 1 gigahertz radio frequencies, so up to about 960 megahertz, I think it goes. And it covers some very popular bands like 300 megahertz band, 400 megahertz band, the 900 megahertz band, 868 megahertz. All of these popular frequencies below 1 gigahertz for low-cost and often unlicensed bands, low-cost equipment operating in unlicensed bands. And it implements certain modulations. It implements amplitude shift keying and frequency shift keying, which is like FM, digital FM, and digital AM. It implements on-off keying, which is just turning on and off the radio, basically a crude AM. And so it's compatible with, and it has a very flexible packet format. So it's compatible with a lot of different wireless ICs, not just things from the CC 1100 family. And that's why I chose it for Yardstick 1, is that it's one of the more flexible parts in this category of wireless transceiver ICs. So we can configure its modem to talk to a wide variety of different low-speed digital communication systems. And we see these types of systems on these frequencies that are supported by Yardstick 1 all over the place. We see them in home automation systems. We see them in industrial control systems. So you might see radio communication protocols that this can interface with in your children's toys. You might see them controlling your power plant. You might see them, say, if you're staying at a hotel very nearby, controlling your curtains in your hotel room. Say at 433 megahertz, approximately 433.92 megahertz, maybe. All sorts of different things in our world around us today have radio communication, low-speed radio communication capabilities that this device is compatible with. So the strengths that these transceiver ICs, like the CC1111, give us, number one is learning curve is so much easier than SDR. I'm going to show you a few commands that you can use using Python on the host computer connected to the Yardstick 1 that allows you to just transmit and receive radio packets very simply without having to learn a lot of theory. And it's very good at dealing with the packet layer or the MAC layer as opposed to dealing with the physical layer. So SDR is really good at the physical layer. Wireless transceiver ICs are more convenient at the MAC layer. And it's very speedy for the reverse engineer to deal with things at the MAC layer. But it does have weaknesses. It only supports certain modulations. SDR can support any modulation. And it can be difficult to reverse the physical layer characteristics, like the precise operating frequency or the modulation or the symbol rate. We're going to use SDR for those things, and then we're going to use Yardstick 1 to try to reverse the kind of the MAC layer. And so we're going to use both for their complementary strengths. And for basically the entire rest of this talk, I'm going to give you a demonstration of a method that you can use using these tools to reverse engineer a wireless system. One more thing before I get into the demo. I just want to mention a couple of things that kind of inspired this talk. Folks who have done research in the information security community over the last year even, using this hybrid approach of both SDR and non-SDR tools. One was presented last year, actually both these were presented last year at DEF CON and a couple other places. And this one was part of Samy Kamkar's talk on hacking remote keyless entry systems and garage door openers, like how to gain entry to a garage and to a car using the over-the-air wireless remote keyless entry systems. And he used the IME, my favorite pink toy that I mentioned earlier, and he implemented an attack on fixed code garage door openers that does a brute force attack in 8 seconds. It's ridiculous. You should check it out. And this is just one of the things that he presented in his talk last year. But as he was reverse engineering remote keyless entry systems for this research, The approach that he used was exactly what I'm showing you today. He used SDR kind of as his initial recon to figure out what radios were doing approximately, and then learn the physical layer characteristics. And then once he acquired those physical layer characteristics, then he turned to yardstick 1, just like I'm going to do today. And he used yardstick 1 to actually, and also some other wireless transceiver IC platforms to implement the attacks. Another one presented last year by Mike Ryan and Richo Healy was their work on reverse engineering wireless communication protocols of Bluetooth skateboards, or actually non-Bluetooth skateboards. Wireless skateboards, in this case, this blog post of Mike's is talking about a non-Bluetooth electric skateboard communication protocol. So they give you a little remote control that you hold in your hand as you ride the skateboard around, and it communicates wirelessly with the skateboard. And what Mike did was the same thing that Samy did. He used SDR, he used a hack RF to do the initial reverse engineering to find out the physical layer characteristics of this protocol. And then he turned to a wireless transceiver IC, and in his case, he used the Ubertooth, because it was operating at 2.4 gigahertz. Now, Ubertooth was originally designed for Bluetooth, but it is a wireless transceiver IC that can do other things. And so Mike wrote some custom firmware for the Ubertooth to help reverse engineer this wireless communication protocol for an electric skateboard. And so he used, again, the exact same hybrid approach, SDR for the physical layer, and then moving up the stack, he used a wireless transceiver IC. So the rest of this talk is a demo, and it's also a review of Stealth Lock, which is a cabinet lock. It's a radio-controlled cabinet lock. And this has a little piece that I can't pull out right now because it's locked. But if I were to unlock it, I'd be able to remove this little piece, and it would, that's the piece that attaches to, say, a cabinet door or a drawer. And you install this thing into the side. It's kind of slim. You install it into the side of a drawer or a cabinet. And then you enter in a pin into this little keypad, which has its own little battery. And you then can lock or unlock this thing remotely. And it's kind of designed for security through obscurity, right? Because this thing is kind of hidden inside a cabinet, and this remote you can hide places too if you want. This could be in another drawer or something, or you can just stick it onto the cabinet door if you don't want to have it hidden. And you have to know the pin in order to lock and unlock it. It's very simple. And so I'll just show you here. If I enter in a code. I'll try to actually unlock it if I remember my code. Right now it's configured with an 8-digit pin, which is the maximum. And I enter in the pin and then I push the unlock button. Totally didn't work. Okay, one more time. 4, 5, 6, 7, 8. Did I get the password right? There we go. Did you hear that click? That click was this thing unlocking, and now I can remove the piece. And so now this goes in and out, snaps in and out. If I lock it again, you'll hear another click, and then it won't pop in and out. But really, we don't need this for most of the rest of the talk. I think that the physical, kind of the mechanical design of this thing seems to be pretty good. My only concern about the mechanical design is how you change the batteries if they run out while it's locked. But other than that, it seems to be a pretty solid design. And but I had a problem with it when I first bought this thing. When I first bought it, I tried doing there's a little procedure to set a pin where you push a button on the lock and then you enter in a pin and you try to set the pin and then you get it, but it didn't seem to be working. The enrollment process wasn't working, and supposedly the default password that it was supposed to ship with, that wasn't working either to unlock or lock it. It didn't seem to work at all. But one thing I noticed was when I put a battery into this remote, keypad, as soon as I put the battery in, this green LED on it would light up for a few seconds, and then it would stop. And then the LED would never light up again, no matter what buttons I pushed. The only time it ever lit up was right when I put it in the battery. And I didn't understand what was going on. So what did I do? I started reverse engineering it. First thing I did was I fired up a HackRF, and I started to observe the radio signal, and I found its signal, and I observed very clearly that when the LED lights up, it's transmitting. And so when I put the battery in, it immediately starts transmitting for a couple of seconds. And then after that, when I'm punching buttons and hitting the lock and unlock and so forth, it never ever transmitted again. It only transmitted right when I put the battery in, which seemed to be wrong. It didn't seem to be behaving the way it was supposed to. So finally, some months later, Taylor and I in the lab decided to get this out and play with it again. And he decided to take apart this remote, since it didn't seem to be working properly. And he had to peel the PCB off of the membrane keypad. They were stuck together. And so it turned out that it basically had buttons held down all the time. Once we unstuck them and put it back together, everything worked fine. When you put the battery in, it doesn't immediately transmit. It doesn't transmit until you enter in a PIN and then press the lock or the unlock button. So while you enter in a number, which is a 4 to 8 digit number, it doesn't actually transmit. But then when you push the lock or the unlock button after entering in a number, that's when it transmits. So it seemed to be pretty straightforward. When I press the lock, it should be sending that PIN with a lock code. And when I press the unlock button, it should be sending that PIN with an unlock code. And ever since we fixed that, this device has worked just fine. So the way that I found its radio frequency in the first place was by cheating a little bit, and that is to use FCC.io, which is just an easy-to-use web interface that Dominic Spill made to help you look things up in the FCC database, the Equipment Authorization Database of the FCC of the United States. The FCC makes a wealth of information available about devices that are authorized, radio devices that are authorized for sale in the United States. Now, unfortunately, I don't know of any other country that has the same kind of level of information that they provide like the FCC does. Fortunately, however, a lot of devices are sold internationally. So you may have a device sold in another country that is also sold in the U.S., and you can still find its FCC ID either printed on the device itself, or you can search and figure out what its FCC ID is and then find it. And when you look something up, you'll get a page like this from the FCC website, and you'll notice that on the right-hand side, it has the frequency, 315 megahertz. This device is authorized to operate in the U.S. from 315 megahertz to 315 megahertz. So that tells me pretty precisely what frequency it should be transmitting on. There's also a link on the left, that detail link, and if you click that, you'll get a bunch of documents that were filed by the manufacturer with the FCC, so you'll get like a test report and all kinds of detailed technical information. I'm going to skip that for today and just use this as a shortcut to find the operating frequency. So I'm just using the FCC for the purpose of finding 315 megahertz. I can find that by hunting around, but this is a little shortcut. So I'm going to now just do demo for the rest here, and I'm going to start with using a tool called, let me increase my font size, Osmocom_FFT. And this is just a fairly simple tool for capturing waveforms and analyzing them with an SDR platform like HackRF1. So right now, my HackRF is tuned to 3.625 gigahertz, which doesn't sound very good. Let's go to 315 megahertz. And let's just punch in something in here and see what happens. I'll set peak hold, so now you get this green line across the top of the frequency domain plot there. So that's just telling us what's going on within this range of frequencies around 315 megahertz. If I type in 0000 lock, oh, you might not be able to see it, but something kind of wiggled around the middle of the screen. I'm going to try to zoom in a little bit. Maybe I'll go to 314.5 megahertz, and I'll just narrow my view. I'll set my sample rate to 2 million samples per second instead of 8 million samples per second. So now I'm looking at only 2 megahertz of bandwidth instead of 8 megahertz of bandwidth. And now 315 is over here. If I enter in a code and press the lock button or unlock button, there we go. We can clearly see the transmission. And one trick I like to do to verify that what I'm looking at is really the device in my hand and not something else around me is I like to transmit really close to the receive antenna. And if I do that, you see how that got a lot higher? Easy way to verify. If you have physical access to the transmitter that you're trying to reverse, easy way to verify that what you're looking at is in fact, what you're looking at in software is in fact the thing you have in your hand. It's just to hold it at point blank range, and you'll see the power level spike like that. So this looks to be like about 314.98. A little bit under 315 megahertz. And some error is expected, especially in lower cost devices. They might have more frequency error. It's authorized to operate at 315, but it's off by a little bit. It's not enough to be concerned about, but knowing that precise frequency of operation can actually help us later. Now what I'm going to do is make a capture and save this capture to a file. And it's very easy to do that by pressing this record button in the lower right-hand corner. So I'm going to enter a code, 0000, and then I'm going to hit the record button and then press the lock button so that it transmits, and then I'll stop. So I get a nice short recording that has my transmission. So I hit record, I press the lock button, it transmits, and it's done. I hit the stop button, and now I have this file. I didn't change its default name, but it's saved here in /temp. So I should be able to see that. I've got this file. It's this one, 3. It must be this 314.5 time, 3.145 times 10 to the 8th power. That's the frequency. So I had this one here from earlier too that I will remove so it doesn't distract me. And I'm going to open up this file in a tool that I like called Spectrogram. And Spectrogram is a tool for visualization of radio signals. It's a newer tool. It's open source software, and it gives me a spectrogram. A spectrogram shows me time on one axis and frequency on another axis, and it shows me kind of everything that was going on in that chunk of spectrum during the period of time that I was recording. And in this case, it shows me time on the horizontal axis and frequency on the vertical axis. So this bright green line across the middle corresponds to that spike that we saw in the middle of the frequency domain plot in Osmocom FFT. So basically, we took that plot, we turn it sideways, and now we have a whole bunch of information here in 2 dimensions instead of just looking in 1 dimension. And if I scroll over to the right, do you see here now I have an event that I can scroll around and see what's going on. And so higher frequencies are further up. So here, this center frequency here, this green line is 314.5 megahertz. That's what I was tuned to. And up here is 314.98 megahertz, where we detected this. And I can zoom in on this a little bit, kind of horizontally zoom, and you can see that this event is made up of individual pulses. They kind of look like an I-beam or something, or like a capital letter I turned on its side, because there's a little bit of kind of frequency spreading when there's this abrupt on-off transition. This signal is turning on or off. But you'll notice if you look horizontally, if I scroll through here, do you see how everything is all lined up horizontally? They're all at the same frequency. Every single pulse is all at the same frequency, which tells me this is not a frequency modulation. But the amplitude changes. The amplitude is represented by the color. And the color goes from this blue background color to this green color when there's an active signal. It abruptly turns on and off. So this modulation I can easily identify visually as being on-off keying, which is a kind of the extreme form of AM. It's turning the amplitude of the radio transmitter on or off. And I can also kind of tell that it's made up of these distinct pulses. If I go starting at the beginning, you can see there's a very consistent pattern at the beginning of a packet, which is a pretty common thing to see, because it's just kind of giving the receiver some time to wake up and to synchronize to these symbols, but it's not really transmitting any information yet. It's just transmitting what we call a preamble. But if I keep going to the right, then we start seeing some pulses that have different durations. There are long pulses, and then there are short pulses, and then we get some long pulses, short. It seems that we're going back and forth between two different lengths of pulses. Do you see that? Some of them are short, some of them are long, but everything seems to be one length or the other. And Spectrum gives us kind of a handy tool to measure these things. I can turn on this enable cursors, and then I can measure the time durations. And I can divide this up into a number of bits or symbols. Let's say I want to go like, I don't know, 10. Then I can kind of move this cursor around so that I can see, look at that. There's a very consistent period of time from the start of one pulse to the start of the next pulse. And it doesn't matter whether the pulse is long or short. And so I'm starting to get the idea that this is a constant rate pulse width modulation built on top of on-off keying. Pulse width modulation means that pulses of one length represent a 0 and pulses of a different length represent a 1. And so I just have a long string of pulses that represent some string of 0s and 1s. And I can measure the bit period here. I can kind of see how long it is by using this little cursor feature. But I also like to kind of subdivide these pulse periods to see what's the smallest time unit that kind of lines up with the beginning and ends of these pulses. So if I double or triple my number of bits, I can kind of see, maybe let's try tripling it. Hey, look at that. If I triple it, do you see how every single pulse period is kind of made up of 3 time units? The long pulses are on, off. 2 on, then 1 period off. The short pulses are on, off. 1 on, and then 2 off. And it's very consistent like this. So I'm going to call these 1/3 of a pulse period, I'm going to call this 1/3 time unit a symbol. And I'll just say that if I were to read this as symbols, and say that an on is a 1 and an off is a 0, then this section that I have highlighted here I would read as 110, that's a long pulse, 110, that's a long pulse, 100, that's a short pulse, and so forth. So I have this string of symbols, 110, 110, 100, 100, 100, 100, 100. And this is how I'm going to configure my yardstick 1 to interpret this waveform, is by configuring it to a symbol rate. And I think I actually have a bug here. Oh, you know what? I forgot to tell in Spectrum what my sample rate was of my capture. So if I tell it that I captured at 2 million samples per second, then it should be more correct. There, you can see that it's about 2,450 bits per second. That's what in Spectrum calls a bit, based on the period that I have specified here. Really, I would call that a symbol, right? I have 3 symbols per bit, and my symbol rate is about 2,450 symbols per second. So it's about the speed of a 2400 baud modem. Okay. So now I know the precise operating frequency. I know the symbol rate. I know the modulation is on-off keying. I've learned all those things using SDR tools. And notice I didn't have to write a single line of code. I didn't have to use any great knowledge of digital signal processing. I just had to know a little bit about how to use these GUI tools to interface with my HackRF, capture a waveform, and analyze it visually. And I've learned all these things. So this is where I'm going to turn away from SDR and try to use these parameters to configure my yardstick 1 to do kind of the next steps of the job. I seem to have forgotten one of my antennas, so I'll just transfer my antenna over to the yardstick 1 and plug this in. And now I'm going to use those parameters that I figured out to configure the yardstick 1. And yardstick 1 is used primarily from a piece of software called RFCAT. RFCAT is some software made by Atlas, and it's specifically designed for this kind of work. And Yardstick 1 ships with RFCAT firmware, but RFCAT also has a host-side component that gives you a Python interface. And it's easiest to use in this interactive Python shell based on IPython. And so it gives me a thing called D, which is my dongle, or my device, my USB device. And I can do things like set the frequency. And I'll set it to 314.980. So that's the frequency in hertz that I observed using Osmocom FFT. And then I'm going to set the modulation. And I'm actually going to use this one, modulation ASK or OOK. That's one setting that implements either amplitude shift keying or on-off keying. We observed on-off keying, so that's what I'm going to use. I'm going to set the modem data rate. There we go. Tab completion for the win. I'm going to set that to 2450. Remember, we observed 2450 symbols per second. So I set those. And those are the main things I need to set. Now, I think I'm going to not have success here picking up this packet, but let's just try it and see. If I do an RF listen, now, okay, you get a bunch of garbage, but let's see what happens when I actually transmit something. I'm transmitting, and notice we're not seeing any packets received. We're not seeing anything other than this garbage that happened when it first started up. Let me transmit it again and see if it does anything. It doesn't do anything. The reason it's not doing anything, probably the main reason, is because what it's trying to do is, there are two reasons. One is that it's expecting that a packet starts with a preamble. By default, the wireless transceiver chip that's on the Yardstick 1 expects to see a preamble of alternating symbols at the beginning of the packet. So it's expecting to see on, off, on, off, on, off, on, off, or 1, 0, 1, 0, 1, 0, 1, 0. And we don't actually have that. If we look back in Spectrum, at the beginning of a packet, what we had was not 1, 0, 1, 0, 1, 0. What we have is, in fact, well, I don't have this quite set up right, but what we have is 1, 1, 0, 1, 1, 0, 1, 1, 0. We have a waltz instead of a two-step. And that is not going to satisfy the Yardstick 1's notion of what a preamble looks like. So what I need to do is tell it to turn the preamble off. And the command here is packet preamble quality threshold. I'm going to set the preamble quality threshold to 0, which says ignore the preamble. Don't expect 1, 0, 1, 0, 1, 0, 1, 0, 1, 0 at the beginning of the packet. And the other thing I need to tell the Yardstick 1 is what to look for to detect the beginning of the packet. What pattern of bits should it expect? It has a default setting that is the default in the CC1111 chip, which is kind of silly because usually you almost always have to set this. So I'm going to set the modem sync word. The synchronization word is the sequence of bits that it's expecting for the beginning of a packet. Now, ideally, most radio communication systems that have a preamble of alternating 1s and 0s, most of the time what you see is they're 1, 0, 1, 0, 1, 0, 1, 0 for some length of time. And then they have a synchronization word, which is a sequence of bits that is not just alternating ones and zeros. It's something that has good autocorrelation. It's something that every packet starts with. You might call it a start of frame delimiter. Sometimes it's called an access code or a synchronization word. In RFCAT, we call it a sync word. And so I'm looking for something to identify at the beginning of a packet. Well, I haven't really identified that yet. I haven't identified that there is a fixed sequence of bits that this thing sends after the preamble that is very consistent. So for now, I'm just going to actually set my sync word to the beginning of the preamble. And so what I should see, if I kind of look a little further here, what I should see is 110, 110, 110, 110. But I don't want to match just anywhere in this waltzy preamble. I want to match the beginning. So I'll put a few zeros at the beginning of it. I'll do something like, let's say, if I put it in binary, I could say 0, 0, 0, 0, 0, and then 110, 110, 110, 110. Let's see, do I have 16 here? That's is that 16 bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I got one too many. And maybe I should take one off from the beginning. So I have 16. Let's see how that works. Sometimes I like to put these in hex, but sometimes it's nice to specify them in binary. This is what it looks like in hex. It's not showing me the leading 0 there, but I've got DB6. So what I'm matching here is some nothing prior to the packet, and then my preamble. That's what I'm configuring the yardstick 1, or I'm configuring the CC1111 on the yardstick 1 to look for, to detect a packet. So now let's try that RF listen. And I'll type 10 or 0000 and then lock. And hey, look at that. Now we're getting something. And do you see how we get a lot of the same stuff over and over and over again? Like DB6, DB6. That's because the number, if you think of those numbers hexadecimal, DB6, that's actually, or 6dB, wasn't that what we set our, look at that, DB6 is what we set our preamble to. So every time you see DB6, that's like part of the preamble, or it's a section of the packet that looks like a preamble. And so we're seeing a lot of repetition, which is interesting, and we're seeing a bunch of stuff that happens every time I push a button. So this time I'll try something else, like 1, 1, 1, 1, unlock. There we go. We're seeing a lot more of the same kind of stuff, a lot of the same hex digits showing up. And it transmits quite a bit every time. And this kind of agrees with what we saw in Spectrum. If I zoom out here, you can see that a lot happens just from pushing the button once. Here's this preamble and then some bits, and then there's a little gap, and then another preamble and then some bits, and a little gap, and another preamble and some bits, and a little gap. And if I were to compare this, I'd probably notice that it's really transmitting the same information over and over and over again. And that's just a crude way of dealing with unreliable radio communications, right? Like, they could use some sort of sophisticated forward error correction or something, but they don't. They just send the same packet a whole bunch of times in a row and hope for the best. And so, that's a cheap and easy way to improve the reliability of a radio system. So it's not surprising that we see a lot of repetition here. Now, I'm not actually a terrific Python programmer, but I'm kind of okay with VI. So I often do things like this. I'll go like copy and paste a hex dump into VI, and then look for patterns. Like I'll search for this pattern, and look at that. You see how I get like the same pattern 3 times in a file? Now, how far into this? This is the, if I look at my counter at the bottom right, 250 characters in, I get a repetition. And then the next one here is at 499 characters in, right? So I have kind of a consistent, every 249 characters, there's a repetition. So I'm seeing that what yardstick 1 is detecting as kind of one packet is really multiple repeated packets. And if I were to use that information then to go in and configure yardstick 1 with a packet length, or I think it's make packet flen, I think it was 30, like 30 bytes long. And then I would do an RF listen, and now it's giving me kind of shorter packets. It's a little hard to read because I'm wrapping around the screen, but some of these should look identical. Now I'm going to use kind of a trick that I like to do with RFCAT, where I'm just going to kind of hackishly just edit files in my RFCAT directory, which is kind of silly. But one of the nice things I like to do with RFCAT, because it's an IPython interface, one of the nice things I like to do is make a little Python program, like just a few lines of Python like this, and then I can run it or load it into IPython and use its functions from the command line. It's kind of like a crude IDE where I can edit things in one window and run them in another, kind of in an interactive environment. So you'll notice all I have to do to create an RFCAT program in Python is to use this import rflib. And then I'm going to make this function called RxSL, receive self-lock. You'll notice I'm doing a lot of the same things that I did from the command line in IPython. I'm setting the frequency, I'm setting the on-off keying, and so forth. I'm setting the sync word to hexadecimal 06 dB, which is the same as what I set it to before. I'm setting that packet length 30 bytes. And then I'm making this little loop here that does basically the same thing that RF listen command does, and it just gives me a slightly different output. So this is just kind of the first step in making my own program to do what I was doing in the IPython command line. And so what I'm going to do is go into my IPython and then do a %run, and this loads that program, and now I can use that RxSL function and transmit a packet, there we go. And now you can see I'm just showing the hexadecimal like 30 bytes at a time of this raw symbol data. And do you see how some of these are totally identical? Like this block right here. And some of them are not because they're shifted over. Basically, I have a problem where that preamble matching, like I'm configuring a sync word to be the beginning of the preamble, but it doesn't take very many bit errors to get a false positive match of that sync word. And since that preamble is so repetitive, sometimes I get a false positive match where I'm just out of synchronization. So most of these are good, like this block right here. Those all line up perfectly together, which is a good indication that they're lined up correctly. But some of these other lines are off by a little bit. So since I have the luxury of this thing transmitting a whole bunch of the same packets at a time, I'm just going to ignore the ones that don't synchronize, right? And the way I'm going to do that is very crude. I'm just going to kind of observe what some of these, I expect to see that at the beginning, and I expect to see that at the end. I'm just going to pick out some bytes that I expect to see at certain times, and I have I'm going to do this in kind of cooking show mode here, and load in a little, what did I call this? Verify? No. What did I call that? Valid. So I have this little function called valid, which is just checking to see if certain bytes match up. And then I'm going to go down and say I'm only going to print out a packet. Was that what it was called? Valid? Packet valid. Okay. If packet underscore valid, my packet, then I'm going to print that it's received. And then I go back over and I rerun that or load that updated code in, and then now you see I'm receiving fewer. I actually got one false positive somehow. Not sure how that happened. But here, when I push something, when I make it transmit, let me try it again. You'll see that it's very consistent. It gets a bunch of packets in a row that are all the same. So that's just a little sanity check that I added in. Now what I want to do is I want to actually decode the pulse width modulation. So instead of 110, 110, 110, I want to see that that's a long, 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 and 100 should be short. So I'm going to take those long pulses and represent them as a 1, and take the short pulses and represent them as a 0, or the other way around. Now, one way to think of that is, if I look here, if I were to, let's say, use my cursor here and line things up, you can see that, is that about right? Or there? There we go. The beginning of every 3 pulses, or the beginning of every 3 symbol periods is always high. It's always on. And the last symbol is always off. So really it's only the middle symbol of that pulse period that contains information. It's either a 1 or a 0. It's either on or off. So I'm just going to use a little bitwise function. I think I called it Decode. So I made this little bitwise function. It's probably more complicated than it needs to be, but all it's doing is going through the symbol data and pulling out every 3rd bit and then concatenating them together into a big integer. And so now, instead of printing out, and I have a little handy cheat here where I'm going to take that line and use this decode function and print that out instead of printing out the raw symbol data. And so now if I load this, I can do 0, 0, 0, 0. Oops, I have to start my receive function. Lock. There we go. This is what it looks like if I'm just taking every 3rd bit. 0, 0, 0, 0, unlock. Aha. You can see only certain parts of the packet changed, right? What about 1, 1, 1, 1, lock? Oh, when I entered 0s, I got Fs, and when I entered 1s, I got Es, which tells me I probably have things inverted, if you think about that. F to E is like counting down, and 0 to 1 was counting up, which is what I pushed. So let me invert everything. If I go into my function where I'm concatenating bits together, and I do something like XOR with 1, so I just flip that bit, then let me try this again, and I go 0, 0, 0, 0, lock. 1, 1, 1, 1, lock. 1, 2, 3, 4, lock. Oh, you can see my byte order is wrong, or my nibble order is wrong, but I'm not going to even worry about that because I can just eyeball that. About 8 digits is the maximum length pin. So let me try 1, 2, 3, 4, 5, 6, 7, 8, lock. There we go. So now we can see, basically I have my order of nibbles reversed. So in my head I see, like, I read those as 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, EA. If I do something like 1, 2, 3, 4, 5, 6, 7, 8, I just entered 8 zeros, lock, and then I do 8 zeros, 3, 4, 5, 6, 7, 8, unlock. So you can see the last byte, the last 2 bytes, which are shown as the first 2 bytes up here. The last 2 bytes seem to be a lock or unlock code, or like an action code, followed by a checksum. And this is a very common sort of checksum. Do you notice the lock code is a 1 and the unlock code is a 2, so that's kind of easy. And then the checksum, when I changed the lock code by just a little bit, or the action code by just a little bit, the checksum changed by just a little bit. which is a good indication that this is a simple checksum algorithm. It's not a more complicated algorithm like a CRC, but it's only an 8-bit checksum, and it looks like it's just a simple like addition or subtraction of all of these things. When I enter in all zeros and then a lock code, which is just 1, I set 1 bit, and you'll notice that the resulting checksum is FF minus 1. Then when I had a nibble that was 2, the checksum is FF minus 2. So it's probably just a subtraction of all of the bytes in a row. So I pretty much just reverse engineered the entire communication protocol simply by using a few lines of Python with RFCAT and entering in some codes and figuring out visually what's going on. So it did take a little bit of programming, but I'm no expert in Python. Like the most complicated thing I did was a little bit of bitwise operation, right? Like pulling a bit out and then concatenating with some other bits. Everything else is pretty straightforward, and most of it I could do right in an interactive command line without even having to open up my editor. So that concludes my demo, and just a few more things to talk about, like what we're going to see in the future to enable even better reverse engineering of wireless communication protocols. I hope I've made the point that this is a powerful approach to kind of use the easiest tool for whatever job you're doing or whatever part of the job is that you're doing. But in the future, we could potentially use just SDR or just these non-SDR tools. And that's an interesting thing to think about because we could have better packet handling capability, like in GNU Radio, for example. We're already starting to see that, but it still takes a lot more knowledge and programming in order to kind of accomplish these MAC layer functions with software-defined radio techniques. So that's something that could be better. We could also see better signal analysis. We're starting to see pretty good signal analysis tools like in Spectrum, but in Spectrum is brand new. And so it's only recently that we kind of have that power in open source software to visualize signals in such a way that it allows us to easily recover the kind of modulation information and data rate and so forth. So we might have better tools for reverse engineering using just the software-defined radio approach in the future. But we might also have better tools for reverse engineering just using the transceiver ICs in the future. In particular, I've talked with some folks about some tricks we could use to use things like Yardstick 1 to do reverse engineering of the modulation and the data rate. But primarily those tricks are things like try a whole bunch of different modulations and see what works, or try a bunch of frequencies and see what works, try a bunch of data rates and see what works, or oversample and then like figure out what the periodicity is and stuff like that. It's kind of hackish. And so in the long run, I think SDR will win. SDR is the greatest tool that you can find, the most powerful tool for reverse engineering wireless communication systems. But as we get there, over the coming years, as we improve our SDR software for reverse engineering, I think we'll continue to find for some time, and maybe forever, that it will be beneficial to use kind of a hybrid approach of both SDR and non-SDR tools. And do I have time for a couple questions? I think I have just a couple minutes. Are there any questions before we go? I know nobody wants to be the first one to ask a question.
Can you use the Yardstick 1 to then transmit what you recorded there?
I could. That's a good question. I could do a replay. So I could do a replay attack. Actually, using SDR, it's easy to do a replay attack. But it's also pretty easy to do a replay attack in RFCAT. And basically the way I would do it, if I go back to my window here, if I scroll back up to like here where I was looking at actually the very first things I was capturing, where I've got like a long string that contained like approximately 3 packets, right, of raw symbol data before I was decoding it. The easiest thing to do is just to tell RFCAT to transmit that. and I can just copy and paste that, tell it to transmit, and do a replay attack. Yeah.
I'm just curious, can you also just brute force the pin?
Oh yeah. So that's one of the great things about using handy tools like Python, is that once I've got a decoding function, it's not much further effort to create an encoding function, right, that does the exact reverse. And then I can, and the only hard part is reversing the checksum. And I think I've pretty much got it, that it's just like a subtraction of all these bytes. And I would just need to verify that by trying a few more codes and making sure I have the checksum algorithm correct. Once I know the checksum algorithm, then it's very straightforward to make a little encoding function that where I can increment or brute force the pin. Yeah, good question. And that's the kind of thing that only takes a few lines of code in RFCAT, but could be a lot more complicated to accomplish with software-defined radio. Any other questions?
Is this tool compatible with the RTL TV tuner?
Ah, yes. So the stuff that I did with the HackRF could have been done with the RTL SDR dongle. The things that I did with RFCAT cannot be done with the RTL SDR dongle. And that's sort of in that category of maybe in the future we can make better tools for SDR reversing. Like we could make something like RFCAT built on top of an SDR platform instead of built on top of a wireless IC platform. That's totally possible. It's just nobody's done it yet. Any other questions? Going, gone. Thank you all for coming.
Happy birthday, Michael!
Thank you, Krishna.